Imagine you're trying to solve a giant puzzle. You have all the pieces, but they're scattered, overlapping, confusing, and sometimes completely hidden. This is exactly what happens when we study complex molecules using traditional one-dimensional NMR. The peaks overlap, the information gets crowded, and clarity disappears. But then, scientists found a way to look at NMR data in not just one dimension, but two dimensions. And this revolution completely transformed how chemists, biologists, and even pharmaceutical industries analyze molecules today. Welcome back to the NMR series. In this video, we're diving deep into the world of two-dimensional NMR spectroscopy, what it is, why it's needed, how it works, and the different types of 2D experiments that reveal the hidden secrets of molecular structures. So while 1D NMR tells us what atoms exist, 2D NMR tells us how they're connected.
So let's discuss why it is important to know 2D NMRs. If you know 1D NMR, the proton NMR, the 13C NMR, but even after knowing these NMR, you need to know about the 2D NMRs. What is the 2D NMRs and why it is so important? So in this video, I'll try to cover out the importance of 2D NMR, and also we will discuss what are the 2D NMR tools that you can use to predict the molecules. The COSY, NOESY, these NMR tools we will discuss today. And especially we will try to understand how you can read these NMRs. If you get these NMRs, how you can find out which peak belongs to which proton and what is the significance of these 2D NMR. Let's see one by one. Let's see this example. Here you can see that we have done a Suzuki coupling reaction, and the possible products for this reaction will be either this or this, A or B, anything. Now if you wanted to know which is your product, the compound which is formed after this reaction, if you want to know, because we can see it here, there's two Cl groups are here, and if the coupling will happen, either this can go to this chlorine, remove this chlorine, and it will form this molecule, or it will remove this chlorine and it will form this bond, right? These two are the possible products that can be formed during this Suzuki reaction. Now with this 1H NMR, it would be difficult to find out which one will be the desired product, right? The H1 NMR of these two molecules will be almost same. It will be difficult because what you can see it here, there is two protons for this and two proton for this. These two will be coming at the same region, right? And this single proton will be at the different region. Here also the same, this single proton singlet this will give the singlet. Here also this will give the singlet. It will be in the another position, and these 4 proton will be 2 and 2 proton will be in the pair in the different region between 7 to 8, right? And here if it is if this R group is CH3, then this CH3 will be around 4, the peak will be around at 4, and this CH3 which is connected directly to this will be around 2, right? So here also this will be the same. So it will be very difficult to find out which one is the exact molecule that is synthesized after this reaction. So in order to find out which molecule is formed, we need to find out a different tool, much advanced than the 1H NMR, and that can be a 2D NMR. Here there's two major 2D NMR that we generally use in our labs. One is COSY, that is 1H correlation spectroscopy. In this spectroscopy, we generally check the adjacent carbons and attached protons, and then we would correlate this adjacent protons and we find out in the NMR. We will see this spectrum, how the spectrum of the COSY NMR look like, how we predict the NMR using the COSY. So first we can see this group, this 2-nitropropane molecule, and this 2-nitropropane molecule will show this kind of a 1H NMR. Here this 3 and 3 protons will be at the same place here, and this the middle one, the second number position proton, will be at the 4 point something position, 4.2 or 4.3 position, because of the presence of nitro group. Now this is clear. If we try to see how it will look like in the 2D NMR, and what exactly the COSY NMR look like, then see this. This is the COSY NMR. Here you can see this. This is what it look like, the COSY NMR. In one, as you can see, there is in 1H NMR, the one axis will show the intensity here, and the other axis will show the ppm value, what you call chemical shift of the proton, right? And here in the intensity. But in 2D NMR, that especially in COSY, both the axis will, this axis and this axis will show the 1H proton NMR. Here also the 1H proton NMR, here also the 1H proton NMR. Both of these two 1H proton NMR of the same molecule will be at the two axes, this axis, x-axis and y-axis, and then we correlate it. You can see it here simply, this NMR. What you can find out here, how you can predict the NMR, that let's see one by one. So we generally draw a diagonal line which is passing through the point, and this diagonal line is what we have to see. So one by one we will see it. First we can see it here at around 4.2. There is one peak which belongs to this 2 proton, right? And if you go to the horizontal, if you draw a horizontal line along this, then you can find out it is getting matched with the one proton, right? Here, this shows that this 2 proton is correlating with the 1 proton. Here you can see in the structure also, this 2 number proton is actually directly interacting, correlating to the C1 here, the one protons, right? So here also, if you go more towards this diagonal, you can find out this 1 protons, which is here, is interacting with the 2 proton, this 2 proton, right? That's how we see that there is a correlation, that they are directly connected. Number 2 proton is directly connected to the number 1 proton. That's how you can see the COSY NMR. Now take one more example. Here, this isopentyl acetate. We can see it here. There is a multiple groups of proton. First, you can see it here. This 336 protons will be at this position around 0.4, 0.5, right? After that, there is a number 2 proton, which is a single proton, which is coming here, and number 3 proton, which is coming here, followed by number 4 proton, which is here because it is directly connected to the oxygen, and because of that it is coming around 4, right? And then this proton, it is actually a singlet proton because it is not interacting with any of the other carbon protons. So we can see this proton is around, because it is connected with the carbon, it will be around 2. So here you can see this is 1H proton. Now if we look this COSY NMR of the same proton, so the same molecule, you can see it here. This is what it look like. These lines I have drawn it to explain you how you predict this NMR. So we can draw first the diagonal line here, as we have drawn it here. Then with this diagonal line we will check one by one. Here this peak is correlating here. If you go into the horizontal, if you draw a horizontal line, you can see that it is interacting with one peak, and that peak belongs to 3 number proton, right? This one, 3 number proton, it is belonging. So this shows that 4 is correlating with 3. It means it is directly related with connected with 3. So here you can see 3 and 4 is directly connected. Similarly, if you can see it here, 3 is also connected to 2 number proton. So we will see that. Once then after that we go further in the diagonal axis, and then we can find out there is one more proton which is showing no correlation, neither on the left side nor on the right side. On the horizontal line there is no correlation, which means that this proton, which is at 2, doesn't correlate with any of the other proton, which means there is no carbon which is having a proton attached to this hydrogen carbon, right? So you can see it here, the 6th number carbon which is having a 3 proton is not connected with the carbon which is having any proton. Like you can see it, this is connected with the carbon which doesn't have any proton. So this clearly shows that this 6 is isolated, this is a singlet. Here you can see that. Now moving further, you can see this 2 number proton. This is correlating with 2, one with 3 and one with 1 number, right? So one with 3 and one with 1 number proton, right? This shows how this correlation, this COSY works, and this is the way you can read the COSY NMR. This is very simple, yet it is very informative, because this shows you in the 2D picture how the protons are connected, correlated. Well, like what is neighbor to the which proton is neighbor to which proton. That is actually the purpose of knowing the COSY NMR. So we can find out which is the neighboring proton, right? This is what we can see it here. Now, if we try to, again we go to this same example, and if we try to find out whether we can distinguish which is the product formed after this reaction by using COSY, whether it is possible to find out or not. Let's see. So this is the 1H NMR. Suppose this 1H NMR is showing that, okay, there is 2 protons which is coming at the same place, right? This one, and these 2 protons are coming here, which is giving the doublet tag, right? And now there is one single proton. These all are belonging to the aromatic region, because 7 to 8 in between the region, this 7 to 8 is a aromatic region. Here you can see this aromatic protons are belonging to this region. So this clears that, okay, 2 to 4 and this 5, these 5 protons are here. But the problem here, the both of them will show the similar kind of a peaks. Like as you can see, these 2 protons here and these 2 protons here are showing the similar type of peak, right? These 2 protons and these 2 protons will show the similar kind of a peak, right? Now this one proton is isolated. Here also it is not connected to anyone, and here also it is not connected to any carbon which is having a proton. So this will not be splitted, and this will give a singlet, right? Here this will also give a singlet. So it will be difficult to find out which is the product by using just 1D NMR. Now if it is not possible with the 1H NMR proton, then we will go to the COSY. If we check with the COSY NMR, can we distinguish between them? Let's see. Now we see this proton which belongs to probably this region, these 2 protons, this is directly correlated with these 2 protons, means this one. So it is clear from the structure also that these 2 are correlating, but means these are just adjacent to each other. Here also these 2 are adjacent to each other, fine. Now this proton single, this one, either this or this one, is not correlating with any of them, right? Which shows that this is not connected to any of the proton which is adjacent, right? So here also this is same. So we can't predict which one, whether A or B is forming with the use of the COSY NMR. That is the problem. Now to find out what we can, how we can find out these, whether this A or B, which is the product formed. To find out that, we have introduced one more NMR, that is a NOESY. This NOESY is actually a nuclear Overhauser effect spectroscopy. In this, we can actually correlate there will be a correlation within the space, which means that it is not necessary to be connected or bonded to each other. It should be very nearby. The 2 protons should be nearby, and the distance between them should be around 5 angstrom. It should be less than 5 angstrom or around 5 angstrom. If it is more than 5 angstrom, the correlation will not sustain. So this means that if the 2 protons nearby to each other in the configuration and the conformation way, if it is nearby, the 2 protons are nearby, then they will generate a kind of a impact on one another, and that impact is recorded and is shown in the NOESY spectroscopy. So basically this type of spectroscopy is used to find out the conformation and configuration of the molecule. Now let's understand what is how we can see the NOESY spectroscopy. Right here we can see that if this A or B, these two are the possible products, and if the product will be A, then these two, the proton here and the proton of this aromatic ring, will be nearby to each other, and because of this neighboring interaction, they will create a correlation, and with this correlation there will be a peak generate, and that they will give the correlation in the spectroscopy, right? And here if you see, there is no correlation between this proton and this proton, because they are in the space, they are far away to each other. So we can see it here whether there is any correlation happening in this in this spectroscopy of NOESY spectroscopy. That if it is there, then this the A will be the desired product, the product which is or which they have extracted, or if there is no interaction, then this is the B product. Now we can see it here in the diagonal axis. This proton which is coming here, a singlet, is interacting with the another proton which is in this region, and you can see this region 7 to 9, between this 9 is a aromatic region. So which means that this singlet which is here is actually this proton, right? And if this proton is interacting with this proton, the another one, which clearly shows that this is the molecule here which is forming and is cleared by the NOESY spectroscopy. So basically NOESY spectroscopy is very useful, and it tells that what is the conformation, what is the configuration of a molecule in nearby. If nearby molecules are getting interacted in the space like this, then we can correlate it and we can find out in the spectroscopy. And if there is no correlation, if they are if they are not spatially near to each other, then they will not correlate and you can't find any kind of a correlation here. Suppose you can see this proton which is around 3.5. this proton will be probably because of this CH3 group, and this is not correlating with anything, right? Here you can see there is no correlation in the left side as well as in the right side, no correlation is there. So this shows that this is single, this is not nearby to any of the proton which is having a distance around 5 angstrom. That's how you predict the NOESY spectroscopy. And now we have learned the COSY and NOESY. I hope you understand how you can find out, you predict the COSY and NOESY spectroscopy, what is the difference between them and why it is useful for us. So if you are a chemist, if you are learning chemistry, if you are just a student or even in the industry professional, then you all must know about these two important 2D NMR spectroscopy. Hope this video will be helpful for you. If you find this video informative and interesting, then please hit the like button. Also subscribe to our channel. And if you are interested to know anything in the field of science or in the field of technology, you can visit our channel, because science is love. See you in the next video. Till then, stay safe, be happy.